Hello. Okay, good afternoon, everyone. Let's start. So first of all, just a reminder, we got a quiz this week, so don't miss it. And we probably will have another quiz next week, but it depends. And if there won't be, if there's no quiz next week, we'll just give the announcement. But at the but the week after the next week won't have any quiz because our final lecture will end up being at Tuesday in that week, and so we want everyone to have more time to prepare your final exam and also the homework 6. Okay. So today we're gonna continue our discussion about confidence intervals. So as we discussed on Tuesday, right? So in practice, we often make some modeling assumption about the random variables we're interested in. For example, we want to model how the stock price varies along with time. I want to model what is the GDP or economic index or whatever. Right? There are the variety of things of interest in our real world, and for which we only collect measurements, a finite number of measurements. And to study the behavior or the pattern of those things of interest, for example, the stock price, the temperature, the climate conditions, and all kinds of stuff, we wish to build up some probabilistic model. And those random variables, we usually assume they follow some distribution. For example, we assume they follow some Gaussian distribution. We assume I follow some, say, Pareto distribution or the exponential distribution. Right? Then the question is, how do we identify the parameters of this distribution? For example, if it is Gaussian distribution, then what does it mean? What is variance? Right? So that's some question we need to address in practice. So the paradigm, right? The statistic, this discipline, right, including machine learning and those kind of stuff, right? The paradigm is that, okay, I'm gonna collect the measurements of those random variables. Then, according to those measurements, which we call sample or sample set, we want to estimate those parameters values. For example, if I want to model how likely I flip this particular coin, I will see heads up. What I'm gonna do is that I'm gonna observe the flipping. I'm gonna flip the coin many times, right? And then I look at the outcomes, right? Maybe I flip them for 100 times. I will like 60 times is heads up and 40 times it tails up. Then I'm gonna, based on those observations, I'm gonna come out some estimate of the probability or the chance that you see it heads up. So that's the basic idea of the estimation and statistical inference. So now, if we dive into a more formal definition, right? Suppose you want to estimate something. You want to estimate the parameter of the distribution F, right, which we believe some kind of things of interest it follows, right? It respects such kind of distribution. We want to know, want to estimate what is the governing parameter for this distribution. And then we do repeatedly doing experiments, or we probably make the measurements multiple times, right? We have collected a set of measurements on those random variables, x1 to x2 to xn, right? So this is called a sample, right? A sample of size n. Then one strategy is that, okay, I'm gonna come out some statistics which is a function over this set of samples, and to derive the estimator of theta, right? That's one way. But doing this can only give you a point estimation. They give you some number, right? You say, according to my collected observations for those random variables, I estimate the mean of f is 0.5, right? If I do this experiments again, I collect another set of measurements over x1 through xn, I get another estimation, which is 0.6, right? So that's not sufficient, because in practice, we not only want a number, right? We also want some chance. Well, we want some kind of range such that I can say, okay, I have a high confidence that my estimate range will cover the ground truth data. So this range is called the confidence intervals, right? So it's not just a number, right? It's just a range. Like for example, if I want to decide whether I'm gonna invest something on some stock, right? Say Apple or Tesla. It's always better to provide that some kind of confidence intervals, like, okay, I have 95% of confidence that the stock price will fall in this range, right? And then I can, according to my confidence interval, and make a decision whether I'm gonna buy stocks or I'm gonna sell my current stocks. So this is the motivation of the confidence intervals. But formally, the definition is as follows, right? So we're gonna repeat the definition we introduced on Tuesday. So we're gonna construct a pair Ln and Un to form our confidence interval. So Ln is the lower bound and Un is the upper bound. So if we can show that my constructed pair, my constructed interval Ln Un has the probability 1 minus alpha to cover theta, then we say my constructed interval Ln Un is 100 times 1 minus alpha % confidence interval. Right? Someone may ask, okay, what is the commonly used alpha choice, right? The commonly used alpha choice is 0.005. That basically means like you want to find out a pair of Ln Un such that you have 95% of chance to include the ground truth parameter theta in your interval. So this interval is called 95% confidence interval. Question? Everyone feels good about this definition. It's not very straightforward, but if we think about this motivation, it's reasonable. Okay, another thing we want to emphasize a lot is that there's something it's confusing. When I was an undergrad student like a dozen years ago, like I was always confused. Is that theta itself is not random. The ground truth parameter theta, you don't know that, but it's some kind of fixed constant. It's not random. The thing that is really random is actually this interval. Why? Why this confidence interval is random? Where does the randomness of this confidence interval come from? Thought? Yeah, but how and why Ln and Un are also random? Oh, yeah. The parameter variation. What do you mean by parameter variation? Well, yeah, as we just mentioned, right? Theta is fixed. Like you assume, okay, it follows. Those random variables follow the same distribution, right? With some unknown parameter theta, right? This theta doesn't have any randomness. It is some fixed constant. We just don't know what the value it is. Yeah, this is very important. So I want to emphasize, right? So yeah, indeed, the randomness of the interval comes from the lower bound, upper bound, Ln Un. But how is Ln Un calculated? It's calculated based on the sample. So Ln and Un are both functions of the n ID random variables in your sample. So if we write it down like more explicitly, your interval is actually two functions of this sample. One is you apply a function, lower bound function over the sample. We got a lower bound, right? And you apply upper bound function, Un, over x1 throughout xn. We got upper bound. So because x1 throughout xn are all random variables, that basically means like, okay, you make an observation, you make a measurement. This time, you got the set of values for x1 through xn, right? You got L values, you got Ln, you got Un values, say 0.2, 0.5, right? Now, if you do another set of measurements or experiments, you observe those random variables again, you got another set of values. And then you evaluate the Ln function, Un function. You probably will get another value for Ln and Un, which could be like, say, 0.15 and 0.48, right? That makes this confidence interval random. It has some kind of uncertainty. It depends on how the variation of those random variables values in your sample will be. Does it make sense? Yeah. So that's why we would say like, okay, suppose this is your theta, right? So if you want to calculate some confidence interval, at the first time, like for example, you do some 100 times of experiments, you got the values of x1 to x100, right? You calculate lower bound, you calculate lower bound, you calculate upper bound, so you got the confidence interval, right? But if you do another round of experiments, I mean, flip the coin for another 100 times, you collect values for x1 throughout xn, you calculate a different interval that could be here and here. So this confidence interval actually varies along with the values of the sample, of your sample, your ID sample set. Right. So what we want is that although this confidence interval could move, right, could change, but we want it has high confidence, that is some designated level alpha, such that this random confidence interval could contain theta with a large probability. Right? That's the key idea. Question? gives what? Why do we use confidence interval when it's random? The reason of using an interval is because we don't want just a point estimate. I don't just want to give a number, like say my estimate of theta is 0.5. I want to give you a range. And because a larger range or a range of the parameters will give you more information. This information can help you better make decision. Like going back to the example, right? We just mentioned, right? If you want to make decision about investment, you just give a point estimate. Say, okay, I believe that tomorrow Tesla's stock price will go to like 228 bucks, right, per share. Of course, this is okay, right? But if another stronger model or some guy will tell you, okay, tomorrow the stock price of Tesla will have large chance to be within this range, say between 220 to 230. Which information do you believe is better or more comprehensive? The latter, right? Because you have a more room to think about, okay, what if, so looks like the stock price has very little chance to below, say, 220. If that's the chance, I think the loss, I can suffer, I can bear with the loss, right? But if it is within this range, I'm gonna make a fortune and I have a larger chance to earn this much profit, right? So if you want to like make your investment model to be very, very powerful and elegant, and you have to make some kind of more quantifiable stuff, right? Rather than just give you a point. So that's the motivation to provide an interval. But here we want to emphasize that because those interval, which we call confidence interval, is computed based on the set of IID random variables. So then they themselves are random as well. That's the nature, right? And that's why when we do different rounds of experiments, your calculated confidence intervals could vary. But what we want is that, okay, one, these confidence intervals to be accurate enough such that it has a large chance to cover the ground truth parameters we want. Does it make sense? Question? Everyone feels good? Okay. So, but if you still feel like uncomfortable, that's fine. You just memorize that the confidence interval could vary. It depends on the value of the sample set, right? Because the value of the sample set could vary. That makes your confidence interval could vary as well. So that's the randomness. That's where the randomness come from, right? But theta itself, like theta, like mean of the Gaussian distribution, the variance of Gaussian distribution, they are fixed and unknown. Okay. So we start with our first concrete example of confidence interval from Gaussian random variables, right? So suppose our sample set, right, x1 throughout xn, they follow some Gaussian distribution with some mu and some sigma square, right? Some variance sigma square. So here we want to point out mu is unknown. So we want to estimate the mean. but we assume the variance is known. So suppose we have collected n ID random variables values, right? And we want to use those random variables to construct a confidence interval such that with 95% chance this unknown mu is included in your confidence interval. Is it clear for everybody? I mean, this problem. Okay, so then the question is, how do we construct such a confidence interval, right? So it just uses some kind of knowledge about the distribution itself. Right? So our method is that I'm gonna use the sample mean. Okay. The sample mean we know is just the average of this n ID random variables, right? And from our previous discussion, we know that the mean of xn bar is what? What's the mean of the sample mean? What's the expectation of the sample mean? Did anyone recall? What? O? Okay. So let us, as we mentioned, right? We assume that each random variable xi in a sample follows the Gaussian distribution with mean and sigma square, right? So now I do some kind of average over the n random variables here. So what's the mean of the average? And by the way, the average is also a random variable. Remember, it's not some fixed constant. Why? Because it is still a function of the n random variables, right? So it's still random. So now what is the mean of the sample mean? Yeah, it is mu. So you can say it immediately by applying the linearity of the expectation. Right? If you calculate that, you see that it is expectation of summation of all xj divided by n, right? So this constant you can move out. I can move out of the expectation. So it's simply the expectation of the summation of those random variables according to the linearity of expectation. The sum of expectation is the expectation of sum is actually the sum of expectation. And so you just calculate expectation for every xi, which is mu across all the, because they are ID, right? So every expectation of xi is mu. You just add mu for n times and divide by n. It will give you mu, right? It makes sense, right? Okay, so we also have the variance of the sample mean as what? What's the variance of the sample mean? Yeah, if you could remember, right, we talk about that, right? So the variance of sample mean is actually the variance of each random variable in a sample divided by n, right? So we make some we made some derivation in last lecture. We're not going to repeat that, but if you feel unclear about this or feel uncomfortable about this, please spend some time after class to replicate our calculation, previous calculation, right? So here we want to point out the sample mean of this n IID Gaussian random variables follows some Gaussian distribution as well. And its mean is mu, and its variance is sigma square On. So basically, it can be written as the sample mean follows some Gaussian distribution with mean still mu and variance through sigma square over n. And as we know, right, the Gaussian distribution has some linearity, meaning that if I subtract xn by mu and divide it by the standard deviation, will follow a standard Gaussian distribution. By standard Gaussian distribution, we mean the mean is 0 and the variance is 1. Any questions so far? Yeah. Zn just comes from some kind of linear transform of the sample mean x and hat, right? And this is you don't need to know why doing some linear transform a Gaussian random variable will end up with another Gaussian random variable. I just treat it as a fact, right? So if we subtract a Gaussian random variable by its mean and divide it by its standard deviation, this transformed random variable, Zn here, will follow a standard Gaussian distribution. Standard Gaussian distribution means that, okay, you gotta have 0 mean and variance as 1. Okay. Everyone's good so far? Everyone's comfortable so far? Okay, so now, why would we look at Zn, this transform random variable? Because we want to first construct an interval which track Zn first, and then convert this interval to the final confidence interval we want. Okay, so we want to find out some critical value, z alpha over 2, right? So we will talk about what does z alpha over 2 mean, right? But we just want to find out some critical value such that the random variable Zn falls in the range minus z alpha over 2 and z alpha over 2. This chance is 1 minus alpha. Right. Let us first put aside the question like how do we identify this z alpha over 2? Let us assume, okay, we have identified a critical value z alpha over 2 such that the probability that Zn is between minus z alpha over 2 and z alpha over 2 is 1 minus alpha. Let's see what will happen. Right? So according to our definition, Zn is such transform of the sample mean, right? So that basically means I have a minus z alpha over 2 less than, I just substitute the definition of x Zn here, right? So it's xn minus mu over sigma over square root n less than z alpha over 2 equals to 1 minus alpha, right? Right? If we know that, right? If we know this is true, right? If we know this is true, that means when I substitute the form for Zn, right? Here we have this guy, right? And then what can we get, right? if we just rearrange this inequality, right? We put it mu in the middle, so we can immediately get, so you can multiply the denominator on both sides, right? And then subtract z n hat. So you can immediately get, you have the x and, sorry, you have the probability. So this inequality is actually equivalent to x and hat subtracted by z alpha over 2, this critical value, times sigma over square root n less than mu less than x n hat plus z alpha over 2 sigma square root n, right? So if we do some kind of arrangement regarding mu, right? So you multiply this sigma over square root n on both sides, right? And then you move x n hat on both sides, right? You can immediately derive that this inequality is equivalent to this inequality, right? That just says mu is between this and this, right? And this probability actually is 1 minus alpha. So this actually construct a confidence interval for mu. You see, the left-hand side is the Ln. The right-hand side is the Un. Does it make sense? Question? Right. So let me repeat again, right? So once you find a critical value, z alpha over 2, which is constant critical value, such that your intermediate random variable Zn falls in a range decided by this critical value, okay? Because Zn is some kind of transformation about the sample mean x and hat. You can rearrange this inequality. You can get a confidence interval for mu only, right? So your Ln, you see, it is constructed through the sample mean. Okay? Ln is sample mean subtracted by z alpha over 2 times alpha sigma over square root n, and Un, the upper bound, is x n hat plus z alpha over 2 times sigma over square root n, right? So you can show that this inequality is equivalent to this inequality. That means the probability of this inequality, which is 1 minus alpha, is also the probability of this inequality, which is 1 minus alpha. So that basically means, okay, we have already found a confidence interval for mu, whose confidence level is 1 minus alpha times 100. Right, that's the whole idea. Question? Yeah, that's a very good question. That one is really harder. We'll mainly introduce how do we estimate our confidence interval for mu. For sigma, that will be a different story. Yeah, but let us assume, okay, right now we know sigma, right? And we want to use those sample mean to find a confidence interval for mu, right? So now it seems like we have already done that. The remaining question is that how do we find out this critical value? Right? And that comes from the nature of the distribution Zn follows. So we know that Zn follow a standard Gaussian random variable, right? So we want to find out the critical value z alpha over 2 such that Zn is inside minus z alpha over 2 and z alpha over 2, this chance is 1 minus alpha. So that actually connects to the quantile, the concept quantile we mentioned before, if you could remember, right? So Zn follows the Gaussian random variable. So if we write down, it's a PDF, right? It will be something like this, right? So it's like bell curve, right? It's symmetric. So this critical value just means that z alpha over 2 just means that if you pick up this z alpha over 2, then the probability Zn is bigger than or equal to z alpha over 2 will be alpha over 2. So what's the probability that Zn is bigger than z alpha over 2? How do we calculate that? That makes us to connect to the definition of PDF, right? So this probability actually is the integration of the PDF from z alpha 2 over to infinity, right? That's the definition, right? So this guy is just you integrate from z alpha over 2 to infinity, and then the PDF of Zn, I'm going to f and dzn. Okay. So we just want to find a position such that if you integrate your PDF from starting this point to infinite far away, the whole area is alpha over 2. That's how we get the critical value z alpha over 2. So why should we pick up z alpha over 2? Because this PDF is symmetric. So if you pick up z alpha over 2, we will know that, okay, this part of area is alpha over 2. Now we pick up another, if you do a symmetric, right? If we look at minus z alpha over 2, right? And then you know that the integration from minus infinity to minus z alpha over 2, which is the probability that Zn is less than or equal to minus z alpha over 2, will also be alpha over 2. That basically means, okay, you got the area here is alpha over 2, and the area here is alpha over 2. So the question is, what's the area here? What's that? I heard that, right? It's just the 1 minus alpha, right? Why? Because your whole area covered by this curve is 1, right? That's PDF, right? So now you know, okay, this part of area is alpha over 2, and this part of area, I mean, the two tilde areas, they take alpha over 2 both, right? And then the remaining area, which just means, okay, your Zn falls in this range, the probability will be right, 1 minus alpha. Does it make sense? Question? Yeah, if you feel like a little bit uncomfortable or feel this kind of like not very intuitive, that's normal. I feel this is not straightforward many years ago as well. That's very common. But you have to change the view, right? So you need to accept the definition of this critical value here. So this critical value just tells you some position such that if you integrate your PDF starting from this position all the way to the infinity, it give you some particular value, which is alpha over 2. And then you use this critical value you can construct an interval such that your random variable Zn falls in this interval, the chance is 1 minus alpha. That's the whole idea. And I recommend you guys like who still feel not very comfortable about this procedure to think about that, right? To repeat this thinking logic to get used to that. You mean which graph? Yeah. Yeah, that's a graph for Zn. That's the PDF. This is a PDF probability density function for Zn. Zn is a standard Gaussian distribution, right? The density is just a bell curve. Right? And once you know, okay, what is this critical value, which might be 1.98, something like that, right? You can immediately substitute its value inside here, and we construct. Then we finish the construction of our confidence interval. That's it. The remaining question would be, okay, how do we know this, right? How do we pick up different alpha, say arbitrary alpha, say alpha is 0.05? How do I know, okay, at which position, what is the value of z alpha over 2, such that this integration is this area, this tilde area is alpha over 2, right? The good thing is that you don't need to worry about that. There are a lot of like libraries, dictionary tells you the values. And here we introduce a very commonly used software. It's called R language or R library in statistics. You just call this command. It's called qnull. And using 1 minus 0.5 times alpha, you will get z alpha over 2. So you put different alpha values, you get the different critical values, the corresponding different critical values. And then once you retrieve those values, you use those values to construct your confidence interval. And that's it. Question? Is what? You mean how is this critical value identified or computed? Oh, yeah, there are a lot of ways of doing that. So basically, this is a kind of like you want to solve kind of equation. You want to solve this. Say, if you assume this one is unknown, right? You want to solve this guy to infinity, and you know the Gaussian, the Gaussian CDF, right? Is something like this, right? X x squared dx, right? You want to solve this equation. It's not very easy to solve, right? So there are like a lot of like numerical techniques to solve that, and the modern computers can give you the capability to solve it very accurately. But even before the modern computer was invented, people have already developed like manually calculation steps. But I can tell you the basic idea is that you're going to discretize this integration. You're going to use some like Riemann integral definition. Remember, Riemann integral definition is like you're gonna partition this axis into many small intervals, right? And then multiply the function value with the length of interval and adds up all the way up, right? And something like this. And then they can arrange this form into some kind of discretized version and try to solve that. So it's pretty complicated. The good thing is that right now we don't need to worry about that because they have already been computed there. You just use some software or some calculator to get that. Very good question. Any other question? Okay, so let's just rest for 5 minutes and then continue. Okay, so let us continue, right? So as we mentioned, right? So we don't need to really worry about how do we get to those critical values for standard Gaussian distribution. People have already developed like numerical methods to compute them. And right now we can use you can either find some statistic book. They usually attach a dictionary and listing a set of common used alpha values and what's the critical z alpha or critical value for alphas. And or you can also just retrieve it from the uh, um, statistical statistic software like R language. This one is the command, right? So if you just search on R online or you just install R library and you just you know in their interface you just type this command, it will give you the number. And once you look, you find a number, you just follow what we have just derived. You can construct the 1 minus alpha 100, 100 times 1 minus alpha confidence interval. This is pretty straightforward, right? So what we really care about is that we need to understand the underlying logic to construct such an interval. That's the most important thing. Okay? So here we give some concrete example, like if you take alpha to be 0.05, that just means like you're gonna construct confidence interval with 95%. Right? Then your critical value z here is 1.96. Right? If you make alpha to be even tighter, like 0.01, that means you're gonna have a 99% confidence interval. Then you got a larger critical value, which is 2.58. Okay. And your homework, if you like, because we won't ask you to do alpha values more different from 0.05, 0.01, you can just copy those numbers. Okay. So those examples are based on the assumption that this confidence interval, right, we just derived, is based on the assumption that in my sample, right, in my sample set of random variables, each random variable really follows some Gaussian distribution. But what if, in general, we don't know what exact distribution our ID random variable follows, right? We just know it's variance. And we still want to estimate the mean of those random variables. What shall we do? The good thing is that we can still leverage the same construction. So basically, we're going to still calculate the sample mean, right? And then subtract it by the critical value from the standard Gaussian distribution and times the variance, the standard deviation, and divided by square root n, right? This is lower bound and upper bound. It's the same thing. We can still use this interval. Why is this the case? This comes from the central limit theory. That's why the central limit theory is so useful and so important. Right? The central limit theory tells us, I remember we emphasized that a lot, right? So no matter what kind of distributions your ID random variables respect, right? If you just average them, and if you just increase n, right? Just increase n, then the sample mean will always behave more and more likely a Gaussian. So that basically means when you subtract the sample mean by mu and divide it by standard deviation over square root n, this Zn will behave more and more like a standard Gaussian distribution. So that means if your n is large enough, so typically n is bigger than say 20 or 30, you can roughly view Zn follows the standard Gaussian distribution. This is justified by the central limit theory, of course. there'll still be some kind of like approximation error, but in practice, it is good enough, right? You can just roughly will your transform sample mean action roughly follows a standard Gaussian distribution. So you can follow this exact same procedure to construct the range that bounds Zn with the probability 1 minus alpha, and then convert it back, you get the same confidence interval for mu. So the calculation is exactly the same, nothing different. Question? Everyone feels comfortable? Okay, so now let us look at some example. Right? How do we construct a specific confidence interval? Right? Suppose we want to estimate the average snowfall in Wasatch Front, right, this year. Right? To do that, you're gonna measure the snowfall at 40 different locations. So you can view that you have 40 measurements, right? So those are RID. So that means you got X1 through X40, right? You have those are just the snowfall at 40 different locations. They are independently and identically distributed. So we assume that we know the variance of those random variables, which is 36 inches, right? So that means sigma square is 36 inches. And after the 40 measurements, right, I calculate the sample mean. That means just the average of these 40 measurements. I get my sample mean as 620 inches. So now how do we construct a 95% confidence interval of the average snowfall? So the average snowfall is actually the true mean of the snowfall, right? The real expectation of the snowfall, if you will, snowfall is random variable, right? So which we do not know. We just random pick up like 40 locations. Of course, they're gonna in the same elevation, right? And I take 40 measurements and I calculate the average of these 40 measurements, which is 620 inches, right? Now I'm gonna use my sample mean and the variance to construct a 95% confidence interval for this mu. We're going to do that. We just apply the formula. Right? As we mentioned, the 1 minus alpha 100 confidence interval is simply the sample mean subtracted by the critical value at alpha over 2 times the standard deviation square root of the number of samples, and sample mean plus the critical value z alpha over 2 times sigma over square root n, right? And now we know that my sample mean is 620. My variance is 36. That means the standard deviation is 6, right? And we have sample size n as 40, right? Now we know that because alpha is 0.05, and then the critical value, right, we just show here, right, is 1.96. So you got the critical value 1.96. Now you just use the formula to construct the confidence interval, which is 620 plus or minus 1.96 times 6 over 40, square root 40. That's it. Question? This is a straightforward application of the formula we have just derived. Everyone feels comfortable? Okay, great. So let us look at another example, which does not seem like a Gaussian random variable as well, but at all. But you see that we can still leverage the central limit theory, all kind of stuff like to calculate the confidence interval. Right? So specifically, we're going to talk about the margin of errors in polls. Right? So you may notice that when you see the results of a poll, right, like a Pew, right, like other polls, right, there's often a statement such like the margin of error for this poll is like plus minus 3%. Right? So what does it mean? What does this mean, and how do they come out with this number? This actually is the confidence interval. It's like your probability plus 30%, plus 3%, minus 3%. This forms a confidence interval. Right? So in more detail, when you make a poll, right, it's like, okay, you're gonna survey a random set of people, right? You probably will just go ahead to ask them face to face or make a phone call, whatever, right? So we can simply view because you got two candidates, right? Let's suppose this is just a presidential campaign, right? So you're gonna support one candidate or the other, right? So you can model and also the people, like any random person will say, okay, I support this guy or I support that guy, right? So you can view their answer, which is random, follows a Bernoulli distribution. It's like, okay, I support, say, Republican, then there's like I flip a coin, I see it heads up, right? I flip, if I support like Democrats, maybe I see the tails up, or vice versa, doesn't matter, right? So, so then the goal of the poll essentially is to estimate the parameter P. This P represents what's the supportness of the whole population for a candidate, right? And you're gonna randomly survey a set of independent people, right? And each one give you an answer yes or no, yes or no, yes no. It's like 1 0 1 0 1 0, right? And now you use those results and you want to estimate what's the chance, what is the probability that the whole population supports a particular candidate, right? And one estimates probability P, right? If this P is very large, say 0.9, then that indicates, okay, most of the people are toward this particular candidate, and he or she will have a larger chance to win the presidency, right? Campaign. Otherwise, or otherwise, the other candidate will win. Any question about the setting here? Okay, so now suppose you have surveyed n personnel, right? And your survey results are RID, meaning that you're gonna have a x1, x2 until xn, right? So each of these people, each of those, each person will give you, yes, I support candidate 1, or 0, I don't support candidate 1, right? So you can imagine you're gonna have a binary result, right? Binary observation for those n random variables. So to estimate the parameter, remember this is a Bernoulli distribution, right? So the parameter is P, which decides what's the probability the candidate 1 will win, right? So again, I'm going to use sample mean. So I'm going to just do the average of all x1 and xn, right? So it's just a summation of those binary responses, right? Xi. I'm going to use xn to construct the confidence interval for P. How can I do that? So first, because each xi follow a Bernoulli distribution with probability with parameter P, right? So now we should recall the knowledge about the Bernoulli distribution. So we know that the expectation of the Bernoulli random variable is P, right? And what is the variance of a Bernoulli random variable? No one remember? What's the variance? The first y, the expectation of a Bernoulli random variable is P. Is what? Yes, right? You just follow the definition, right? So the Bernoulli random variable can only take 1 or 0, right? If you take the average, if you want to calculate expectation, it's just the probability it takes 1 times 1 plus the probability it takes 0 times 0, right? So this guy, no matter what's the probability of being 0, you multiply with 0 is 0, right? So the only thing is here, right? So the probability you take 1 is P, right? That's why the expectation P. Right? You can use the same framework to calculate the variance, which we're not gonna do this again, right? We did this in our previous lectures. So the variance is P times 1 minus P. Right? So now we talk about the sample mean. So what's the expectation of the sample mean? In other words, what's the expectation of the average of n RID Bernoulli random variables? What's that? Yeah. Yeah, it's still P, right? And what's the variance of the sample mean? Yeah. So the variance is the variance of each individual random variable divided by the sample size, right? So this is a common conclusion, right? Applied to any set of ID random variables. So it's just the P 1 minus P over N, right? And now we're going to leverage the central limit theory, right? You see that although x1, x2, until xn, they follow a discrete distribution, right? They're just a 1, 0, 1, 0 sequence of 1, 0, 1, 0, those kind of stuff, right? But their average, the sample mean, can still asymptotically follow a Gaussian distribution. So that basically means, okay, if your n is large enough, you can basically view your sample mean follows a Gaussian distribution with mean P and the variance as P 1 minus P over N. And based on that, you can construct a 95% confidence interval for P, which is here. X accent hat plus or minus 1.96. And remember, this guy is the standard deviation, right? Does it make sense? Any questions so far? Okay, so now we haven't linked the so-called the margin of errors, right? So the margin of errors actually is just this guy. It's the sample mean plus or minus something. So it's like, okay, I'm gonna survey 1,000 people, and I do this average, right? I know, okay, it's a supportiveness maybe is a 0.56 or 54, right? Or 54%, right? Now I have a margin error plus or minus 3%. So where does this 3% come from? It come from here. It's actually it's just the half of the interval length. This interval is centered at the sample mean, right? So this is called a margin of error in the post, and this is how those numbers in the report, the poll report comes from. One interesting question is that, okay, if you know P, right? If you know some P, and if you know some N, then you can immediately get the margin of error, right? By calculating this guy, right? You can immediately get, say, if the two candidates has equal support, like P equals to 0.5, right? You just survey 100. That means your margin of error is 0.098. That means basically it's around 10%, right? That's pretty large, right? Then someone will ask, okay, if I want to control my margin error, I want my margin to be as small as possible, to be, say, to reach some particular level of margin error, say 3%. What should we do? We can just set this margin error to be 0.03 and solve it for n. You see that when P equals to 0.5, meaning the two candidates are kind of like equally supported by the population, right? And then if I still want to get a 3% margin of errors, I need to make n to be as large as 1,036. Oh, sorry, 67, right? So that basically means, okay, you have to survey a lot of people, right? Not just randomly ask 10 friends. Okay, so let's stop here today. We'll continue our discussion on next Tuesday.